So one of the first things you probably learned in a geography course was Tobler's first law of geography that states the objects or things that are closer together are more related than things that are distant from each other. And this is really important with spatial regression because this concept violates the assumption that your data points are independent of one another. Because data points are related to other data points that are close together in space, it violates that assumption. So we need a way to detect the spatial autocorrelation within a data set in order to account for it within a spatial regression model. So what exactly is spatial autocorrelation? It's really a fancy word, and if you break it down, you'll understand that it's not so intimidating. So the root word is auto, in that in Greek means self, and correlation, as you know, means a relationship between variables. So autocorrelation describes when a data set is correlated with itself, or a variable's data points are correlated with themselves. And in this case, they would be spatially correlated with themselves based on Tobler's first law of geography, that data points in a variable that are close together are going to be correlated with themselves. So in spatial analysis, it's important to classify data points as being either randomly located in space or non-random, so they're either clustered or dispersed. Randomly located points in a data set would indicate that the data value seen at that location could be any other location, that the data point isn't being influenced by its location in space. On the other hand, non-random data points would indicate that space is having an influence on the data values seen at that location, that there's a trend or a pattern that exists within the data set that can be explained by space. So when we measure spatial autocorrelation, we either get a positive, a negative, or a zero value of our spatial autocorrelation. So if we have a positive spatial autocorrelation value, we know that the points in the data set or areal units are being clustered together, so similar values are seen as closer together. If we have a spatial autocorrelation value that's negative, we know that the points or areal units are dispersed throughout the study area. And lastly, if we have no spatial autocorrelation, it means that the pattern is random and that the values are arranged randomly throughout space. So in a random pattern, you could have points that are clustered or other points that are randomly dispersed. It's just a mix of clustered and dispersed randomly throughout space. When you're looking at a variable plotted in space, it is almost impossible to understand a random pattern because our brains as humans has developed to pick out patterns that we see. And a random pattern is sort of a mix of clustered and dispersed at the same time, and thus it's nearly impossible for us to detect a random pattern without some sort of mathematical model. So an example of positive spatial correlation would be a plant species that prefers certain types of environmental characteristics, and you see a patch of that plant species growing in its preferred conditions. Another example would be housing prices within a city. You're most often going to find clusters of very expensive homes or very low-income homes, since the value of a location influences the cost of a house. In terms of negative spatial autocorrelation, so when a pattern is spaced out or dispersed throughout a study area. One example could be the home range of predators within that study area. So if you're looking at, say, bears throughout a study area, you're most likely to see that they are very spread out throughout a study area because they like to hunt in their territory, and other predators tend not to overlap their home range or the location where they like to hunt. Specifically in Canada, as opposed to somewhere like the United States where healthcare is more privatized, in Canada, you will often see hospitals dispersed throughout a city so that they are only servicing one location and not overlapping with other hospitals that do the same thing. Now, a weak or zero spatial autocorrelation example is very, very hard to come up with because it's almost impossible to find a random pattern in the built or natural environment because most things are based on the influence of location. The best thing that I could think of is plotting points on a map with a random number generator. Although spatial autocorrelation can be a problem for simple linear regression, it's actually a very good thing to see in a data set. If you're looking at a spatial pattern and you find positive spatial correlation within your variable over space, it means that there's something driving the pattern that you see. So that pattern or trend that you're seeing can help tell a story about why that variable is located in the way that it is throughout space. So for example, if you're looking at lung cancer rates within a major city, you would probably find positive spatial autocorrelation. And if you're looking at a map, you would likely see a cluster of high lung cancer rates near, say, a factory that's emitting pollution in that area. On the other hand, you might see a cluster of low cancer rates around a place like a park where the air is much more clean. So spatial autocorrelation doesn't have to be a bad thing. It's actually a very good thing in geography. As a geographer, you are looking for spatial autocorrelation to help tell the story of why you're seeing what you are seeing. So if we want to create a spatial regression model at the end of our research, we have to first identify spatial patterns within our dataset. So the method you choose depends on the type of data that you have. So the first type of data you might have is point data, and the other type of data you can have is aerial data. So if you have point data, you can choose between nearest neighbor analysis, quadrat analysis, or Moran's eye. On the other hand, if you have aerial data, you can either do a join count analysis, or you can also use Moran's eye, just like in the point pattern analysis. So with point pattern analysis, you are essentially trying to understand if the data points in your study area are dispersed or clustered. An example of this would be if you're looking at a disease in a study area and you found the data was clustered, that may indicate that in those locations you have outbreaks of that disease. So first we're going to talk about the nearest neighbor analysis to detect spatial autocorrelation within point data. So this is a quantitative method that has the ability to analyze point patterns within a study area, and it uses distance between points to determine the spatial pattern being seen. The nearest neighbor method can be used to calculate what's known as the nearest neighbor index, which can then be interpreted to determine the spread of points within your study area. So you can see in this picture, there is a data set, or the points within a variable plotted in these gray markers. And you're essentially looking for the distance between each point and its nearest neighbor, and you're calculating or measuring the distance between those 2 points. So for the point letter A, you are looking for the nearest neighbor, which is notated by the gold line, and you are taking that distance, and that's the distance to its nearest neighbor. For point B, you're doing the same thing. You're just looking for that nearest neighbor, the nearest point to the B location, and you're taking that measurement as a distance. And then point C, you're looking for its nearest neighbor and measuring the distance, and that is its nearest neighbor. And you go through that entire data set of gray points, and you're doing that for every single data point. And based on those distances, you can calculate the distance, or the observed average distance, by summing up all of the nearest neighbor distances for your data set and dividing by the number of points or data points within that data set. And that will become your observed average distance. And then you need to know the average nearest neighbor distance within your data set that could be expected based on a random distribution. In order to calculate that, you take 0.5 and multiply it by the square root of your study area, so the actual area of your study area, and divide that by the number of data points within that study area. Then once you know the average distance by random chance and your observed average distance, you can divide the observed average distance by the random average distance. And that's how you will create the nearest neighbor index. So here's an example of 4 real-world examples where they've calculated the nearest neighbor index. And you can see on the other picture on the right in the slide the interpretation of that index value. So you can see the fire stations has the highest nearest neighbor index, which would indicate that fire stations are the most dispersed within the study area. This makes sense because there aren't as many fires within the city, so they don't want to overlap service areas because it would be a waste of public resources. Police, on the other hand, although it's very similar to fire stations in that they don't want to overlap service areas, they do need more police support within higher population areas. So as you make your way downtown, you'll likely see that there are more police stations to accommodate the higher population. So you're getting slightly more clustered for police stations rather than fire stations. Schools, interestingly, has a value that's close to 1, which would indicate a random process. It's not exactly random, though. It is based on many different demographic characteristics, such as age or where people actually live. So there are processes driving the location of schools within the city, but if you're just looking at it alone, it does, at least in terms of the nearest neighbor index, look random. Now, voting locations, so locations where you'd go to vote in federal or provincial elections, are more clustered than the other 3 examples. And this is likely because in the same way schools are located throughout space, voting locations are based on demographics, but also placed at central locations that can service the public. So typically when you are looking at the nearest neighbor index, you'll be using a program to calculate it. And in this case, the picture here is from Esri's ArcMap, and the hypothesis testing states that the null hypothesis is that the point pattern is random, and the alternative hypothesis is that the point pattern is not random. So it's either clustered or dispersed. And they calculate the significance of the nearest neighbor analysis based on the z-score distribution. And you can see the output there shows the z-score that was calculated for this particular nearest neighbor example. And you can see the critical values there. So it works the exact same as the z-test, where if the z-score is greater than the critical value, then it is considered significant and you can reject the null hypothesis. In nearest neighbor analysis, you can also see that if the z-score is less than the critical value, or towards the left of the normal distribution, it is considered clustered. Whereas if the z-score value is toward the right and greater than the critical value toward the right side of the distribution, it's considered dispersed. And if it doesn't achieve statistical significance, the pattern is considered random chance. There are two main issues with nearest neighbor analysis. The first being the calculation is very dependent on the actual boundary of the study area. So where are your data points in relation to the study area boundary? So if you consider the same point pattern, the same data set with two different study sizes, you can see that the larger study area will have a lower R valued, which means it's more clustered, whereas a smaller study area would have a higher R value, which means it's more dispersed. And you can look at the calculation and exchange different area values to see how this works. The other issue is that this type of point pattern analysis does not consider the local variations within the study area. So there could be areas within the major study area where the points are being clustered together or more dispersed, but overall it's just showing one nearest neighbor index score. The next method to detect spatial autocorrelation with point data is called quadrat analysis. Quadrat analysis examines the frequency of points that are occurring throughout a study area based on a study area divided into cells. This method examines the variability between cells and their theoretical value within the study area. The resulting output is called a variance mean ratio, which is also abbreviated to VMR. And if you have a VMR that is close to 1, it's considered a random pattern. If you have a VMR that's close to 0, it's considered a dispersed pattern. And if you have a VMR greater than 1, it's considered a clustered pattern. So you can see in the picture on the slide, there is the point data set in your study area. And in this case, the study area is a black square. And then you divide the black square or your study area into cell. And then you divide your study area into cells. And you count the number of points within each cell to then determine or calculate the VMR score. So the next 3 slides are examples of different types of patterns and how to calculate the variance mean ratio for each pattern. So you can look at the picture and then look at the table to determine how to actually calculate the VMR score. But in the end, you can see the random pattern here has a VMR of 1.1, which is very close to 1, and thus it shows a random pattern. In the second example, we have a perfectly dispersed pattern, and its VMR is 0, which obviously means it's perfectly dispersed. And in the last example, we have a clustered pattern, which shows a VMR of 8.9, which is greater than 1, thus it's a clustered pattern. And in each of these three examples, you can see how the numerator and the denominator of the variance mean ratio calculation affects the outcome in the end. So when we're doing hypothesis testing for the variance mean ratio, the null hypothesis is that the point pattern is random. Whereas, again, the alternative hypothesis is that the point pattern is not random. So it's clustered or dispersed. Now in quadrat analysis, we are basing our hypothesis testing on the chi-squared distribution. So here is the random and clustered example from the previous slides. And based on the chi-squared distribution, we have 10 quadrats within the study area. So there's 5 rows and 2 columns. So that's 10 quadrats. So 10 minus 1 is our degrees of freedom. So we have 9 degrees of freedom. Our significance level is 1. And thus, based on the chi-squared distribution table, we know our critical value is 21.6. So for the random pattern, x is the number of points per quadrat minus the mean or average number per quadrat, and then you square that number and you sum all of them together. We know that's 20 because if you look at the table from the previous slide, you can see the sum of all of those numerators is 20. And the average number of points per quadrat is, again, 2. So then 20 divided by 2 is 10. So 10 is our test statistic for the random pattern. And as we just discussed, the critical value is 21.67. And since 10 is less than 21.67, we cannot reject the null hypothesis. So in other words, the point pattern that we're seeing seems to be a random pattern. And on the other hand, the clustered example, we know the numerator is 160. We know the denominator is 2, so 160 divided by 2 is equal to 80. And you can look at the table for this pattern to look at where those numbers are coming from. And because 80 is greater than 21.67, we can reject the null hypothesis and say that, well, since it's greater than 21.67, then we know it's clustered. There are 2 main issues with quadrat analysis. The first one being the actual locations of the points within the cells. So where are the cells dividing those points? Because it matters. If you look at that picture as an example, you can see in those 4 quadrats, the 2 cells in each quadrat are dispersed in the left picture, but on the right picture, the points are clustered. But because the way that they're divided into these 4 quadrats, basically the quadrat analysis sees these 2 examples as being the same thing. Because there's simply 2 points per quadrat, and it doesn't understand that in the right side example, they're actually clustered together, whereas on the left-hand example, they're dispersed. And again, with quadrat analysis, local variation is not considered when they're creating the analysis. So some points could be clustered, whereas others could be dispersed throughout the study area, and it doesn't understand that. Another problem with quadrat analysis could be that your cell shape choice or the cell size can mislead the readers. So when you alter the shape of your cells, which could be either nefarious or just that you're using something other than a perfect square lattice of cells. So if you're looking at neighborhoods within a city, you know that the shape of the neighborhoods is not always the same. So a great example of this is called gerrymandering, which is when a political party changes the administrative boundaries to alter the results of a vote. So essentially, gerrymandering is when a political party will alter an administrative boundary in order to encapsulate more of their political voters in order to gain favor in the overall vote. So you can see in this picture, this is the exact same point pattern in all three examples, but the cells are different, the shape and size of the cells are different, and thus it shows a different frequency per quadrat. When you're using area data, you have to use other methods to analyze these spatial autocorrelation. So the most simplistic form of detecting spatial autocorrelation with area data is called join count analysis. This gives us the ability to describe the degree of clustering or dispersion in a data set with binary data. So first, raster data is essentially when you take a study area and you divide it into pixels or cells. And binary just means having two parts. So binary data is often represented by either a 1 or a 0, where 1 is the presence of something or yes to some sort of question, and 0 is representing that it's not present or that it's a no to some sort of question. So for example, if you were looking at the suitable habitats for turtles, you would go through the grid, and for each cell, you would indicate a 1 if yes, it is suitable for turtles, or 0, no, it's not suitable for turtles. So in the picture, you can see the different types of spatial patterns and how the binary data will look or influence the output. So in order to test the significance and calculate the join count analysis, first we need to know what the expected number of black and white joins are. So black is a 1 in this case, and white is a 0 in this case. The expected number of black and white joins, so locations where a black cell is located adjacent to a white cell. So the sides of the cell or shape are touching. So the expected number of black and white joins is calculated by taking 2 multiplied by j, which is the total number of joins in the study area, so total possible number. You multiply that by the probability that an area will be black. So you're just looking at the data at face value and counting the number of black areas and dividing it by the total number of areas or cells. and then multiply that by Q, which is the probability that an area will be white. And in the same way, you're just counting the number of white areas, dividing it by the total number of areas in the study area. So here are 3 different examples. All of them have the same number of cells and the same number of black and white areas. So the orange lines are indicating locations where there is a black-white join. So if you count up the number of orange lines where this is showing a black-white join, for study area A, our observed black-white joins is 24, because every single spatial join in this pattern is a black-white join. And you can see in the study area B that the number of black-white joins is only 12, because there's only 12 locations where a black is adjacent to a white. And in B, in study area B, you can also see the blue lines are indicating the number of black-black joins, and the green lines are indicating white-white joins. Really, we're only interested in the number of black-white joins. But I thought I would show the black-black and white-white joins just so you're kind of on the same page. Probability of a black area is calculated by counting the number of black areas and dividing it by the total number of areas. So in all 3 cases, there are 8 black cells and there's 16 total cells. So it's a 4x4 grid, so that's 16. So the probability of a black area is 50%, or 0.5. The number, or the probability of a white area, is the exact same, because you're just counting the number of white areas. In all 3 cases, it's 8 divided by 16 cells, which is 0.5. And again, there's 24 total joins possible. So if you look at all of the joins, either black-black, white-white, or black-white, they will always total 24 in this case. So based on that, if we're doing hypothesis testing, our null hypothesis is that our observed black-white joins is equal to our expected black-white joins. Or in other words, the area pattern that we see is random. The alternative hypotheses are, 1, that the observed black-white joins is not equal to the expected black-white joins. So we're just looking to see that the area pattern is not random. Or we could look at the observed black-white joins are greater than the expected number of black-white joins. And in this case, it would show an area pattern that is dispersed. Or we can look at the observed black-white joins is less than the expected black-white joins. And in this case, it would be clustered. So if we're looking at our examples, we can see the expected black-white joins for all study areas. So the study area A, B, and C, in all cases, the expected black-white joins is 12. So if we gather and summarize that information into one chart, we can see that in study area A, we can reject the null hypothesis that the observed black-white joins is the same as the expected black-white joins. And we know that based on the alternative hypotheses that this data is dispersed. In study area B, we can see that the observed and expected black-white joins is the same, and thus we cannot reject the null hypothesis because it's random. And in the final example, study area C, we know that because the observed black-white joins is smaller than the expected, we can reject the null hypothesis and say that this data is clustered. The last method of detecting spatial autocorrelation that we'll look at is called Moran's eye. Moran's eye has been around since 1950, and it's a very popular method to identify spatial autocorrelation for both point and aerial data. You can see based on the calculation shown in the slide that this method of detecting spatial autocorrelation is much more complex, and it bases its calculation on the distance between each cell or point and every other cell or point within the dataset. The output of Moran's eye is very similar to Pearson correlation coefficient, and it's also very easy to understand, which is probably helping the reason it's so popular. So if your Moran's eye output is a 1, it indicates that there's a strong degree of clustering. So high values are near other high values, or low values are near other low values. If your Moran's eye is -1, it indicates that your point or area data is highly dispersed. So high values are close to low values, and low values are close to high values. If your Moran's eye is 0, it just means that your data is randomly placed throughout the study area. Since the calculation for Moran's eye is much more complicated, we will just discuss the outputs that you would see from a program such as ArcGIS. So if you're hypothesis testing, your hypotheses would be as follows. So your null hypothesis is that Moran's eye is 0, which would indicate a random pattern. Your one-tailed hypothesis for the alternate is that Moran's eye is greater than 0 and thus clustered. The other one-tailed would be that Moran's eye is less than 0 and thus dispersed. And a two-tailed test would be Moran's eye doesn't equal 0, so it's either dispersed or clustered. So if you're looking at a data set which looked like the picture in the slide, your Moran's eye output would be -1, which you know is dispersed. Your z-score would be -7.59, and your critical value at a p-value of 1% would be -2.58. If your alternate hypothesis was that the data is clustered, so Moran's eye is greater than 0, based on this output, you would fail to reject the null hypothesis. And if your alternate hypothesis was that your data was dispersed, so Moran's eye is less than 0, you would reject the null hypothesis in this case. And also if your alternate hypothesis was that Moran's eye just doesn't equal 0, so it's either dispersed or clustered, you would again reject the null hypothesis. One of the benefits of Moran's eye is that not only does it have a global measure of spatial autocorrelation, but it also has a separate local statistic that you can use to test local variation or local dispersion or clustering within your dataset. Moran's eye is the most popular among these methods, and it has many variations of the model that can be used for different datasets. So since spatial autocorrelation violates the assumption that data points are independent of one another, we cannot use linear regression. We can use geographically weighted regression modeling to account for the spatial dependence within your data to help understand how much explanatory power your independent variables have on your dependent variable. Not only can you understand the explanatory power of your independent variables, you can understand this relationship throughout space in your study area. So as I briefly discussed with Moran's eye, there are what is known as global versus local models. So a global model assumes that the data set is constant throughout space. So a global model will often smooth the prediction surface to look at the trends in the overall study area. They're not concerned about the localized variation within the data set, as can be seen in this picture. The global models will just be concerned about the overall or average trend within the data. And a local model will take into account those local variations or areas or groups of data within your study area that have different trends than other groups in the data set. So a global trend could be something like the hours of sunlight in all of Ontario, whereas a local model might be used to predict crime rates in a city. So you'll have pockets of high crime rate and pockets of low crime rate dependent on your location within the city. So then furthering that, we have what is known as stationarity or non-stationarity. So stationarity assumes that the properties of a population don't change over space or time. And this is the basis for a global model, that the properties or parameters of the model aren't changing, and thus you have just one trend through space. Whereas most spatial data has non-stationarity, which would indicate that there are local variations in the properties of a population throughout space. So we can use something like geographically weighted regression modeling, which is abbreviated to GWR, to understand the model predictions through space. So in this regression model, it allows the parameters of the model to change over space. So you're essentially creating a new regression model for every point or aerial unit within your study area. So each aerial unit or point within the data set will have a different regression model for that location. The regression model changes based on the distance from the point of interest or location to other points in that data set. The GWR model has inverse weighting, which means that points that are closest to the location of interest will have the highest weights because they are most influencing that location, and points that are furthest away will have a lower weight applied to the model because they have less influence over the model. Generally speaking, GWR models are not seen as strong evidence to suggest a certain spatial pattern or to create predictions, but it's more used as an exploratory tool to help guide the researchers' recommendations and discussion points. So you can see in this diagram and slide, the regression model is built for each data value within the data set. So in this case, we are creating the regression model for point A, and we're looking at the distance from point A to all other points within the data set. And based on the distance, we're assigning a weight to that location. So for shorter distances, the weight is much higher because it's closer and thus has more influence over location A. So in this specific example, point M would have the smallest weight because it would have the least influence over point A. Whereas points E, H, and I are the closest points to A, and thus will have greater influence or a higher weight in the regression model. So you would actually go through all of the points in this data set and do this, create a new regression model for each point. But just as a secondary example, if you're building the regression model for M, you would have C and D weighted the least because they're the furthest from point M and would have the least influence over M, whereas points L, I, and H are closest to point M and would have thus a higher weight because they influence that location M more. So once you've gone through each location and created weights, then you can create your regression model. In some cases, you're not actually looking at the location of interest and using every other point within the data set to create the regression model. In some cases, you'll use what's known as a window, which is a location or distance buffer around the point of interest, where you'll only use points within that window to create the regression model. So on the left-hand side of this picture, we have a fixed kernel window, which means that the window doesn't change in size, but the number of points within that window may change based on the location on the map. On the other hand, we can use an adaptive kernel, which changes the window based on the number of points within the window. So an adaptive kernel will always have the same number of points used in the calculation to create the regression model. So based on this approach to create a geographically weighted regression model, we can understand how the predictive power of the spatial regression model changes throughout space. So we can understand the predicted value, but we can also look at the R-squared value or adjusted R-squared value throughout space. And based on this output map, we can have a better understanding of how the parameters of the model or the independent variables influence the dependent variable throughout space. So as an output of the geographically weighted regression modeling, you can map the parameter coefficients, so the independent variables, and you can see the pattern of where high or low values are located throughout space. And then you can compare those parameter coefficient maps to the R-squared or adjusted R-squared map that shows the predictive power of each regression model throughout space. So you can see how well the parameter coefficients or independent variables are able to predict the outcome of the dependent variable based on the location in your study area. And this can be a very powerful way to understand your data and how location influences it throughout space.